Morning, everybody. I hope that, let's see, did I post the exam topics? I did, right? Did I ask that last time? Yes. I'm getting older. And then GRASP tomorrow, did I post this announcement, right? GRASP is switching rooms, and we got to switch twice just to allow the Women in Engineering Day to happen, which is a fantastic event. So we're more than happy to have to switch rooms around so that they can do their thing. But yeah, it'll be the computer lab, NS 126 in the first part of the morning. And then after 9:30, we'll move to the bigger physics lab once the class that's in there gets out. So watch out for that. We were in the midst of AC circuits, right? And I had basically just dumped a toolbox on you, told you it was all lies, and that's okay, we're just going to do it anyway, right? And I just want to clarify, this isn't the normal lie that we tell in this class where we say, oh, look at all the physics we're doing, and then we ignore all the hard parts, right? It's kind of baby physics. We're actually doing what electrical engineers do. If we're simplifying anything for physics 2B, it's the fact that we're only doing series circuits, right? But we also do that for the physics 4B students because doing anything in parallel requires rederiving a bunch of things. So this is how it works, right? And we're dealing with it. We did an example of sort of how to work our way through a circuit. I want to do a couple more examples and then get into applications of AC circuits, things that you see in your everyday life where AC is really important. So we'll just continue along that theme of doing examples, showing you how to use this toolbox, organizing the information, and so on. Well, the last example will be with everything in the circuit. This particular circuit has only two elements in it. Well, three if you count the generator. Let's see, what do we got? We start with the AC generator, right? And what's the first thing we run into? This resistor. So we got a resistor. And then finally, this inductor. An inductor is a solenoid. It's a physical circuit element that uses Faraday's law and hence Lenz's law to slow down the rate at which current changes in a circuit. It acts a little bit like a capacitor but with magnetic field as opposed to electric field. All right, so we got our resistor, we have our inductor, we've got our AC generator. Let's see, this one's 20 volts. And a frequency of 60 hertz. All right, so what the heck do we do? So what that we have all of this information? Where do we start in any of these circuit problems? Not just the resistance, but the equivalent resistance, right? We got to find the whole resistance of the circuit. In AC circuits, we give that a different name. Symbol Z, does anybody remember what it was called? Impedance. Yeah, impedance is what I like better, but impedance is how it's pronounced, right? So I usually, because, I'm not even sure what they're asking for. I'm just going to calculate it because usually we need it, right? In the end, right, we're looking for current, right? And we're going to get our current by knowing our voltage and our equivalent resistance or impedance in an AC circuit. So we got to find that. It's the square root R squared quantity plus quantity XL minus XC squared. So to be able to pull that off, I do need to find out what my inductive reactance is. Right? Reactance is a fancy word for we're faking it till we make it. So we're going to turn everything into a resistor, right? This inductor is magically, and it is kind of magic, going to have units of resistance, ohms, okay? If we pull off the right calculation, right? 2 times pi times F times the value of the inductance. So that's 2 times pi times 60. And then what am I going to put in for the inductance here? What's an MH? Right up here. 255 MHs. Milli for the little m. And capital H is Henrys. And again, it's just the unit of inductance. So I've got to put, what do I write? 255 times 10 -3. Good, right? And this, I mean, again, don't worry that a Hertz times a Henry is a ohm. Like, just believe. Just really go with it. It's much easier. I got 96.1 ohms when I did all those calculations. I reserve the right to not know how to use my calculator and get the wrong answers here. The process is correct. All right, so back to the impedance. So like problem solving method, right? AC circuit, identify what you've got, find the impedance, right? You're going to need it at some point to calculate something, right? And then once you know the impedance, try to figure out what they're asking for and see what you can get. All right, so 525 squared plus 96.1 squared. What's XC in this problem? Yeah, it's 0. It's 0 because there's nothing there, right? So we can just do that. And then, all right, so this should, just a side note, what does that look or feel like? The square root of something squared plus something squared? Feels like Pythagorean theorem, and that's because that's what it is. It's the Pythagorean theorem that comes out of the phasors, which are rotating vectors, which help us to understand what's really going on in an AC circuit. So again, don't worry about that, but there is a pattern to the madness. I got 533.7 ohms. And then from Ohm's law up here, my current is going to be my voltage divided by my impedance. 20 volts. How do I know that's RMS? No, because it just gave me the voltage, and you assume in AC circuits that if they just give you a voltage, it's RMS voltage, right? It would be, if it were max voltage, they would have said maximum voltage or peak voltage. They would have indicated something. Okay. All right. Assuming I can calculate it correctly, I got 0.037 amps, 375, sure. 375 amps, which is 37.5 milliamps, which is probably what Wiley Plus will annoyingly want me to answer. Again, process is visualize, strategize, do it, check it, right? Your visualization is draw a picture of the circuit. Your strategy is find the impedance and then figure out what else they want you to find, which usually means you have to find some reactances. And then finally solve for what they're asking you to solve for. Current through something, whatever. It can be a lot of different things. Yeah?
If there's more like resistors, do you just add the resistors?
Yep. Yeah, if there's like a second resistor in here in series, let's say the second resistor is 100 ohms, you would just add 525 and 100 together. You can just squish the resistors down, yeah. If there's more inductors, you can do that. We tend not to do that. We tend to just give you one of each, because anything else is kind of dumb. All right. All right. This problem, okay. So visualization, right? Okay. They tell us it's an RLC circuit. These last ones didn't really say, right? They just sort of listed what the things were. But when you see RLC circuit, it means a resistor, an inductor, and a capacitor, right? And we can tell that, whoops, where'd it go? There we go. We can tell that by the fact that they give us resistance, they give us capacitance, and they give us inductance, right? Okay, so let's draw out our circuit. We've got our AC generator, and then we have a resistor, we have an inductor, and we have a capacitor. Don't panic if the book draws you a circuit that's got those out of order. It's all the same thing, right? In series, you can put them in any order as long as they're connected one after the other. So I got my resistor, got my inductor, got my capacitor. Not going to worry about what they want me to find because I just need to find impedance. I always need to find impedance. XL minus XC squared. Okay, so that means I have to find these two things. 2 pi f times L and 1 over 2 pi fc. So this is 2 pi 60. You'll see 60 quite often. Why? That's what United States does. If you're in Europe, it's 50. Right? You can do others, but those are specialized situations. All right, L. Okay, so L is 25 mH. So what am I going to write? 25 times 10 to the minus 3, because that little m literally means times 10 to the minus 3. And I'm going to get a number out of there. I got 9.425 ohms. All right. Oh, no. Ah! It all died. Wow, it died early this time. Let's see if I can get it to come back. Yesterday or Wednesday was fine.
That's good.
All right. Technology is grand, isn't it? All right, let's see. Is it doing something on the screen? 2 pi 60. Okay, and then my capacitance is 0.15 watts. That little mu symbol means what? -6 farads. And when I put all that into my calculator, I got 17,683 ohms. I usually carry, several sig figs in intermediate calculations just to make sure I don't get round off error. All right, calculate the impedance. 9.9 kilo ohms. 990, yeah, I just moved the decimal place 3 places. Squared plus, and here we're going to go 9.425 minus 17683. All right. We're going to get a number out of this in just a second. I got it right here. But let's just talk for a second. Looking at this impedance, how much is the inductor affecting this circuit compared to the capacitor or the resistor? So what's the resistance of the resistor? So about 10,000 ohms, right? Okay. What's the resistance of the capacitor? It's about 18,000 ohms, right? And what's the resistance of the inductor? Like 10 ohms. So compared to 10,000 and 18,000, is 10 ohms really going to do anything? No. Okay, so you can kind of read into what the relative strength of these different elements is, just based on their effective resistances, right? This circuit is dominated by the capacitor, right? Resistor is helping, dominated by the capacitor. Inductor is doing very, very little in here. I got 20,257 ohms. For my impedance. Okay. Now that I've got my reactances, I've got my impedances, right? It's time for me to find out just what the heck they're asking me to do. Find what? Voltage. Where?
Across each element.
Okay. What the heck does that mean? That means they want me to find the voltage across the resistor. The voltage across the inductor and the voltage across the capacitor as sort of single things in the circuit. Back when we did a DC circuit, we were able to do this, right? We did the thing where we did series and parallel and kind of brought it all down to a single optimized, equivalent resistance. Calculated the current coming out of the battery for the entire circuit, and then worked our way backwards. So we're going to do something similar, but a whole lot easier. We're going to find the current that's coming out of the generator. We can do that because we have the impedance. We have the overall resistance, so we know that the current coming out of the generator is going to be the voltage divided by the impedance. Where did I get that from? I equals V over Z. What equation is that? That's Ohm's law, right? So I just didn't bother to do it. I did algebra in my head, which is dangerous. All right, so 115. So this is just standard wall outlet. 115 volts at 60 hertz. Divided by my impedance, 20,257. I got 0.0057 amps, or 5.7 milliamps. Okay. So that's the total current coming out of the AC generator. What is the current through the resistor? The same, because it's in series, right? Okay. What's the current through the inductor? The same, because it's in series. What's the current through the capacitor? The same. So we know the current and resistances of all of these elements. So if I'm going to find the voltage across the resistor, I'm going to do the current times the resistance of the resistor. If I want to find it through the inductor, I'm going to do the current times what? The, air quotes, resistance of the inductor, which is X sub L, right? This inductive reactance. And if I want to find the voltage across the capacitor, current times X sub C, the reactive capacitance, or the capacitor's reactance. You can say it either way. I've seen it written both ways. Language being what it is. 0.0057 times, and what number am I going to put in here? 9,900. Okay. And then 0.0057, what number am I going to put in for the inductor? 9.425. And then 0.0057, and then what? 17,683. So this is 56.43 volts. This is 0.054 volts. And this one is 101 volts. So there are the voltages across each of the elements in this RLC circuit. Is anybody feeling a little uncomfortable about these answers? Is there something wrong? Don't see it? What happens if you add all those voltages up? Yeah, they don't add up to 115, right? Voltage is really close to energy, isn't it? Right? And so it should be conserved. You shouldn't get more voltage out of your circuit than you put into it. This voltage, what did we just calculate? What kind of voltage did we just calculate? RMS, this sort of statistical average of what it is over time. But in fact, in this circuit, right, the voltage is constantly shifting and altering through all the elements. I promise you that any one instant of time, like if we just looked, right, the total voltage across all three elements would be 115. Remember, these represent an average, an RMS value. They're not what is actually happening at an instant of time in the circuit. These are more like, yeah, this is what happens most of the time kind of idea. Okay? But while the resistor has like voltage, positive voltage in it, the capacitor can have a lower or negative voltage in it. There's complicated relationships between all of these things when you start looking under the hood, which is why we usually we don't check our answers by saying, well, it should only add up to 115. That's true in DC, but that's not true in AC circuits. AC circuits, we kind of have to go, okay, well, we hope this works, and then you go out and measure it, and in fact, it does, and we can power homes. We can do all that kind of stuff. I gave you a few more equations in the toolbox, and I'm not demonstrating their usage. Annoyingly, physics textbooks have this desire to make you calculate things like the power factor, which is cosine phi, right? So if you're asked to find the phase angle of the circuit, which is the angle phi, just do one of those, right? Okay. These aren't hard or difficult like calculations to do. Once you've got the impedance, right, you can calculate your phase angles and power factors and whatever. Okay. I won't demonstrate that, but we do have to talk about one more of these equations that I haven't shown or talked about or done anything with, right? Okay, which is this interesting one that is a frequency. Okay, and it's got a special. It's called F naught, right? And we usually put a sub-zero or a sub-naught on something when we're talking about what? Initial. Yeah, like an initial. Here it doesn't mean that. Here it means the resonant frequency of an AC circuit. Okay, so I learned kind of a different way of writing this. Remember, so from your book, even though I just looked at it, I can't remember it anymore. Your book writes it like this, 1 over 2 pi square root of LC, which is fine. It works just fine. I learned 1 over the square root of LC. But see how mine's in omega? Okay? There's a reason that omega is the better thing to do, even though really the only difference is that, right? Okay, which means that there's a problem somewhere in the math.
It should be 1 over omega.
It should be 2 pi. No, that's right. F equals omega divided by 2 pi. I can do math. I can do math in my head sometimes. All right. But whatever way you want to do it, you can stick with the box, okay? What the heck is resonance doing here now? And does anybody remember what resonance was?
That was like when you had like the multiple things on a standing wave.
Yeah, okay, so this goes back to waves, okay? Resonance was something we did right before we did standing waves, but this is back in Physics 2A. So I'm committing the sin of having you try to remember something from last semester, right? Okay, so quick review. Resonance is an increase in amplitude of an oscillation when you give it energy or you give it a push at the frequency it wants to oscillate at. That was a really long sentence, so let's make it easier. Resonance is swinging on the swings. In my class, I did a little demonstration. We didn't have a swing, so I simulated it, right? Okay. But if you're on the swings and you're swinging back and forth, when do you pump? Like when do you add that energy to increase the amplitude of your swing? Like it's Is it on the way back, or is it as you're turning around and starting to move forward? It's right at that, right? And you got to learn the technique, don't you? I love watching little kids get on the swing for the first time, right? They sit down, right? And then they get upset and mad that the swing's not going anywhere, right? Okay? You can't pump or add energy at random times. It has to happen at the right time. The frequency at which you add that energy, the number of cycles per second that you do that, okay, is called the resonant frequency if it matches what the swings want to do. So you're trying to achieve resonance when you're swinging on the swings. What does that look like electrically, right? So we've got the physical sort of swing or a pendulum or a mass on a spring sort of bouncing back and forth. And if we like push right as it's turning around, we'll get a bigger amplitude of oscillation, right? So electrically, don't panic. I know this looks horrible, and it is, but it's not, okay? An AC circuit is the electrical version of the swings. It's the electrical version of a mass on a spring. It is a harmonic oscillating system. And we'll talk about why we want electricity to oscillate harmonically, right? But let's concentrate just a little bit on all of the springs and masses, right? Just as kind of a little bit of a review, right? So what do we call that maximum displacement? That's the amplitude, right? Okay. And it should, be equal on either side, right? And what's happening at amplitudes? Yeah, the speed is zero. This is where it's the mass on the spring's turning around. Okay. So if we start a mass over here, right, we let go, it accelerates and achieves its maximum velocity at equilibrium. And then it continues to go until the spring gets compressed and it stops. And then the spring pushes it back, right? And it passes through equilibrium. And then this process repeats, right? In a circuit with no resistance, so this is an idealized case, we take the resistor out and all we have is a capacitor and an inductor, okay? If we start with that capacitor fully charged, it's been charged by an external battery and then that battery has been removed, okay? What's that capacitor going to want to do with all of those charges that are stored on it? Yeah, it's going to want to, right? These positive charges and these negative charges want to do what? Move which way? I mean, they can't go this way. There's the capacitor, this is a gap, right? So they can't physically move that way, right? But what do positive and negative charges, when they're connected to a wire, want to do? They want to meet, right? Okay, all these positives want to go this way. All these negatives want to go this way, right? So they can neutralize out. They want all their dance partners, right? So that means as the positive charge flows out, there's going to be a current, right? Okay? But there's a solenoid in the way. There's a bunch of loops of wire. And what's the flux through those loops of wire to begin with? Zero. Remember Faraday's law of electromagnetic induction and Lenz's law? What did they have to say about an increasing flux? They want to decrease it, right? So why is there an increasing flux? Well, now there's current in the wire, and this current is flowing through a bunch of loops, right? And those loops are going to create magnetic field, which creates magnetic flux in itself, and that changing magnetic flux is going to be fought. Remember, a solenoid or an inductor in a circuit works to slow down the rate at which current is changing in the circuit. So as that capacitor begins to push, right, and it's like, I'm going to get these charges out so they can be together, current happens in the circuit. But the inductor says, There was no current before, and I want no current now. It's always going to lose to the capacitor. But that current starts flowing, the inductor fights or slows down the rate at which that current can flow until the capacitor is fully discharged. And now that the capacitor is fully discharged, what's going to happen to the current in the circuit? The capacitor was pushing, push charge, but now it doesn't have any charge to push with. So what happens to the current? It goes to zero, right? But the inductor has been fighting the increase all along, and now suddenly there's a decrease in the current in the circuit. So now what's the inductor going to do? Remember, it fights the change. So while the current was increasing, it's trying to slow it down. But now that the current is decreasing, what's it going to do? It's going to try and keep it going. And so you end up with this current flowing out, developing a magnetic field in the inductor, which then continues, even though the capacitor has been fully discharged, continues to push current and hence charge around, and in doing so, ends up reversing the polarity on the capacitor and fully reverse charges the capacitor from before. We're halfway through our oscillation because now the inductor doesn't have any more magnetic field in it. There's no way for it to push or fight or do anything. This capacitor is fully reverse charged from where it started. So what's going to happen? Yeah, now the current turns around. Solenoid goes, ah, right? Okay, fights it, helps it until we're back to where we started. And now we're back to where we started. So what's going to happen? The process is going to start all over again. What we have is an electrical version of a pendulum, of a mass on a spring, of a tick-tock. What is this? It's an electrical clock. Okay? The frequency of this clock is given by that equation right there. So this means that if you want to time 1 second, right? If you want one cycle to happen every second, you're going to have to go figure out your inductance and your capacitance to make that happen. Why would you want to time 1 second? Oh, right? Or maybe you want to time a millisecond or a mic. You getting the idea? Right? We can set up any frequency we want. But this goes way, so this is an oversimplification of how electronics do time. Okay? And I don't want to get into the nature of time right now, but simply put, electronics don't do this. Okay? There are timing circuits in electronics. Computer processors use a timing circuit. It's often referred to as the speed of the processor, and they'll say that the processor works at 5 gigahertz. What did they just tell you? What's a hertz? It's a frequency, right? 5 gigahertz is 5 billion cycles or 5 billion operations of this circuit, this timing circuit, in 1 second. Okay? And it's not true anymore that that means a single calculation. Processors run things in parallel and do a whole bunch of neat stuff now. But the whole point is that the timing circuit for the processor is at 5 gigahertz. And that's kind of the rate that it expects. Now those rates will fluctuate with power demand and a bunch of different things. The motherboards that exist in our phones and computers, they run at different frequencies for various reasons, most of them having to do with thermodynamics and quantum mechanics. And so you have to match up a lot of these frequencies that exist. But most electronics today either get their timing circuit from a quartz crystal, actually. It turns out that the natural frequencies in the mineral quartz are fairly stable for measuring time. If you let a computer just do like a LC oscillation, it'll throw off its time by like 1 second every hour. It's actually pretty sloppy because there's lots of electrical noise and there's lots of things that can change inductance and capacitance in a circuit external to the circuit. It's really hard to sort of harden a circuit to keep capacitance and inductance the same because it fluctuates with temperature and all that kind of stuff. And so quartz crystals are used, but more and more nowadays, instead of having a physical like element in the circuit that's giving the frequency timing pulses, electronics just give up and ask the internet. Okay? Because the internet has access to the best clocks in the world, which are atomic clocks. Okay? Atomic clocks count the frequencies of vibrations of cesium atoms, although I think we have a new standard now and I can't remember what the atom is. Suffice it to say, an atomic clock only loses 1 second every billion years or so, right? So they're hyper accurate and allow a lot of the technologies. So our phones know what time it is because they just ask the internet every few minutes, every hour, right? What time is it? And they adjust their internal clocks. Because the internal clock of this thing is going to, left by itself, will be off by like 1 second every hour. Okay? And so it just asks, what time is it? Adjusts the timing and everything works fine. Okay?
So if I had it disconnected to the internet for like days?
Yeah, it'll be off.
That's cool.
Yeah. I don't know exactly what Samsung and Apple and all the phone makers are doing right now to alleviate that, right? But basic circuit technology will always be off by a lot at the end of a day. Like I've seen circuits go off by a full minute at the end of a 10-hour shift without an external timer to sort of regulate the electronic circuit. So we're not talking about resistance in here, okay? Because as soon as you add resistance, that's a whole nother ball of wax. But time, there's no excuse for being late anymore. What is everybody's phone doing? Being exactly the same time. Growing up, I could say, oh, I'm sorry, I'm late. My watch was off. Because we all had physical timing circuits in our watches, and you would every day have to adjust your digital wristwatch, right, in order to get it back onto some sort of time. You could call on this ancient device called a phone that was attached to the wall. You could call, and a computerized voice would tell you what the exact time was at the beep. Yeah. Yeah. What was the number? 555 popcorn?
What?
Yeah, I think maybe there wasn't a zip code required, or an area code required. It might have just been popcorn. You just spelled popcorn out on the keys, and it would be the timing signal that, in this case, AT&T over on the West Coast, the timing signal that AT&T was sending to all of their computers across their networks. So, yeah. Sorry, little trip down memory lane there. What does this have to do directly with you and not ancient technologies? What do you okay, sorry. Speaking of ancient technologies, right? Okay. But it's actually not as ancient as you think because you actually use this every day. Matter of fact, I can see one from here. What is this?
Radio.
This is a radio antenna. Okay. This particular antenna is designed to pick up AM and FM broadcast signals, right? For radio for sound, right? But the antenna I can see from right here that you guys can't. Jenny, can you see it? It's way out there next to the cloud. What is that way out there? You know what that thing looks like? It looks like a little mushroom with things sticking off of it.
I don't know what that is.
You don't know what that is? That's a cellular tower. Okay? And what is a cellular tower? Bunch of radios. Okay? It's a bunch of radios. We'll start simple and we'll get to your cell phone in the end. Okay? Adjusting the radio dial is doing what? What do we call that process of trying to get to a radio station that you want to listen to?
Changing the frequency.
Mr. Bale, I have no idea what you're talking about. I just go to Spotify. Tuning. You tuned in to the frequency you wanted to hear. So there's a bunch of different frequencies, and nobody understands if I say 101.7 FM anymore, right? Okay, right? Or right? There was all these different frequencies, and the radio stations would say, you're listening to 101.7, 99.8, smooth jazz, right? Like whatever it was they were doing, right? Okay. And let me ask you a question. An antenna on your car, an antenna on your phone, how many radio stations is it picking up? An antenna is just a wire. It's just a wire, right, that's being exposed to how many radio stations? All of them is the answer, okay? Every electromagnetically generated broadcast, okay, going invisibly, right, in the radio spectrum, will be received by your antenna. It receives all radio stations at the same time. So how does the radio know which station you want to listen to? You turn a knob, which changes a capacitor that changes the natural frequency of the circuit. If your radio's natural frequency, resonant frequency, matches the frequency of the station you're trying to listen to, what happens to the amplitude of the swing? It gets really big. And so you hear only that station. Back in the day, you drive up and down 99 or something, and there'd be like a point halfway between like Bakersfield and Fresno where two stations were broadcasting on the same frequency, and you'd hear both of them. Christian rock and rap simultaneously, right? Okay. That's because both stations were about the same distance away, and they were both on the same frequency, and so the radio would be like, that's the one you want to listen to? I'm just going to magnify, I'm going to resonate with whatever right? And you'd hear both stations, right? There's a bunch of rules that the FCC would imply to make sure that radio stations didn't step on each other, but it would happen anyway. Because depending on what's going on in the atmosphere and the sun that day, it can change the ranges and distances. So what does this have to do to you and not these ancient technologies? What's Bluetooth? It's a mystery, isn't it? Because sometimes it works and sometimes it doesn't. Okay, right? What's Wi-Fi? What's LTE? What's 5G? What's 5G UW? What are these things? I don't think about it, Mr. Baylor, as long as it works. They are all wireless signals, aren't they? They're all different frequencies of radio waves that are being picked up by your phone. Your phone has I found this picture. I was like, I got to include that one, right? Dang, that guy or gal, like, holy cow, right? Okay. Ham radio saves lives. You go, brother. All right. Your phone has a bunch of antennas in it, okay? In fact, somebody mocked up a picture once of like a phone that with all of its antennas, right? They had like a satellite dish and a wire. Like they just had it looked ridiculous, right? Okay, and of course it wasn't true because the antennas that they put in are put in around the outside edge of the device. How does each antenna know what to get? If antennas are just wires, and they're picking up all of the radio waves anyway, then how does the phone know that a Bluetooth signal is a Bluetooth signal and a Wi-Fi is a Wi-Fi and all that kind of stuff?
Can they only pick up their signal and that's it?
No, they pick up all of them. This is the thing. Every antenna has no choice. An antenna is just a wire. And there's going to be a radio wave that comes along and jiggles the charges in the wire. So how does it know which one to listen to? Resonance, natural frequencies. Bluetooth's natural resonant frequency as specified by international agreement and technical documentation. There's a Bluetooth standard. Bluetooth is a copyrighted technology name, right? So any device that wants to use Bluetooth has to pay the Bluetooth Consortium, or whoever owns it, a fee to license that particular technology and the frequencies that it operates on. Same thing goes for Wi-Fi. Okay? Wi-Fi operates either at 2.4 or 5 gigahertz, the access point that's right there. Okay? That little whitish box, not the speaker, but the one, and not the one with the blue light. That's fire suppression system. But that access point is emitting a bunch of different frequencies depending on whether your device can support 5G or 2.4 gigahertz. 2.4 gigahertz, by the way, is the same frequency that microwave ovens generate. So that if in your house there's a time, it seems to be like every day my Wi-Fi just sucks, okay? Somebody's running a microwave somewhere, probably. What's happening is your device is operating on 2.4 gigahertz. Somebody turns on a microwave somewhere in the apartment complex. There's a bunch of noise now in the 2.4 gigahertz band, okay? And your device is getting confused. If you're on LTE or 5G, those use anywhere from 2.4 gigahertz all the way down to 900 megahertz. 5G, weird, does something different. But have you ever noticed how 5G or 5G ultra-wide doesn't seem to go very far? Like, it can be really fast, but it's not a really long distance signal. When you get outside of town, right, it usually like falls away from 5G and goes to LTE. The LTE is a slower, it runs at a different frequency. The higher the frequency, the more information per second that can be sent. But the shorter distance the radio wave can propagate through air or buildings. So it's a trade-off, right? You can get high bandwidth, but not very much distance. Or you can get low bandwidth with being able to go a really far distance, right? So, but yeah, I mean, this is all directly related to the alternating current circuit theory, right, that we've been studying. Of course, it's a lot more complicated than what we've done together. But none of this would be possible without Faraday's law of electromagnetic induction, without an understanding of Lenz's law, without knowing about magnetic fields and the connection between magnetic fields and electric fields. It all starts coming together, right, in these applications. And please, please don't ask me why Bluetooth doesn't work all the time. The answer is because. Okay. Actually, okay, there's a little bit more to that answer. Sorry, I'm going to a little bit of a tangent here. Bluetooth is doing things today that it was never initially designed to do. Bluetooth was never meant to carry the amount of bandwidth that we're asking it to do, right? Put in your Bluetooth headphones or whatever, send music, lossless, right? No compression, whatever. Bluetooth simply wasn't designed for it, okay? And it's kind of, you know how human beings are. Somebody gets a licensing deal and gets entrenched and then nothing ever changes. It's kind of like what Bluetooth's doing, okay? There's Bluetooth 4, there's Bluetooth 5, there's Bluetooth 5.1, there's all these different standards. You may or may not have heard of like Wi-Fi 6, Wi-Fi 6E, Wi-Fi 7, now there's Wi-Fi 8, okay? These are all the same standards bodies putting out new standards so that everybody knows how to talk to each other, right? So that Apple and Samsung can talk to the makers of the access points or whatever, right? You need to have these industry standards. The problem is it's kind of hard to break into these standards and markets and things like that when something's already been established. Even if you have a better way of doing it, right? You've got to fight for the bandwidth and the frequency spectrums that are controlled by actually international agreement, right? The FCC is responsible in the United States for making sure that, you know, Wi-Fi 6E that runs on a 5 gigahertz band doesn't step on Wi-Fi 7's implementation of it, blah, 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 blah. But really, you need to be able to do this internationally because in our modern world, what do people expect when they step off the airplane and they pull out their phones? Right? They expect for it to work, okay? And we expect for them to work too. I would contend that this device is probably the most important device to have nowadays in our modern society. It's almost eclipsing like needing a car, right? In terms of your ability to get paid, to pay things, to look up information, right? All that kind of stuff. They really have become a ubiquitous, even necessary piece of technology. Just a function in our modern society. Just like ever since the 1940s in America, you've had to have a car to be able to do anything in life. Our cities are designed with the idea that people will commute rather than live and shop and play and work all in this small area. We live outside, we come in, we do all right. It's just part of urban planning, and it's starting to change a little bit, but it doesn't change very fast. Our modern society has gotten used to this idea that people are going to have a cell phone. To the point now, oh, you want to unlock your apartment? Forget a physical key, right? Got to have your cell phone. That's it. We're done. Woot! With all of Unit 2, right? Let's got a little bit of time left, and I could let you go early, but why would I do that? Physics 2B. Let's not do, the 2A students are taking a test today. So be nice to them.
Oh, so you want us to give you more time?
No, it's fine. I'm ready. They're not. But I am. This is really small, and I don't have a really good way to magnify it on the screen. So what's going to happen on Monday? Lab. We're going to do Faraday's Law lab. Okay, we're going to just try and make sure we wrap our brains around Faraday's Law, okay? And then what's happening on Tuesday? We're going to review, and review means you come and ask me questions, otherwise you're just going to get stupid jokes or something, right? So, yeah, no. And then Thursday we're going to take the exam. These are the topics for the exam. What are your questions like about the topics? I'm not going to start physics. I'll do that on Tuesday. But do you understand what you might be asked? Like circular motion of a charged particle in a magnetic field. What does that mean? Like, what are the possible topics or questions that I could be asking when it comes to that? Anybody remember anything where we did? Thank you, Esteban. It's true, right? Esteban does remember, and most of you don't either. The mass spec. The mass spectrometer, okay? This is a mass spectrometer type question, okay? May not be about a mass spectrometer, right? But notice I didn't say it was conceptual. So this is a calculation, right? Find the radius, find the mass, find the magnetic field that this charge is in, right? So it's a calculation question. You're calculating something using an equation, right? But be prepared to be able to handle the circulation of a charge in a magnetic field. Magnetic field from a current carrying wire. We didn't do any of that, right? Remember, I think I remember the equation. Let's see, is it mu naught I over 2 pi r? Where r is the distance from the center of the wire, right? So, and we did other problems where there's maybe 2 wires and we had to add or subtract the fields. So, how do you know whether to add or subtract fields if there's 2 wires? I can calculate the magnitude, mu naught I over 2 pi r. I can get a number. But how do you know? Okay, so even if it doesn't say conceptual on it, do you think you might need to use the right-hand rule? Yeah. Sorry. Right? Okay. Josh is going to kill me now. Right? The warning on this exam is they're all conceptual. I mean, that's usually the case anyway, right? But really, right-hand rules play a huge part in being able to apply the equations that we have, right? So just because it doesn't say conceptual doesn't mean that there's not going to be conceptual elements or right-hand rules in it. I did call out, right? Right-hand rule, force on a moving charge. I'm letting you know that you will be directly tested on which rule?
Right hand.
Which of the right-hand, thank you. Which of the right-hand rules?
Oh.
The handshake, right? And I'm telling you right now, you'll also need the hitchhiker. Not on that problem, but everywhere else. Faraday's law doesn't say conceptual, so you're going to end up calculating there. But where do right-hand rules rear their ugly heads in Faraday's law? The answer is Lenz's law. So there's a separate question where I'm going to ask you to predict clockwise or counterclockwise, right? Okay. Which way is the current flowing in a loop of wire based on whatever's going on, okay? On that problem in particular, well, on both, right-hand rule, force on a moving charge, and Lenz's law, both of the conceptual ones, there's really no partial credit. Like, it's really difficult for you to explain to me what you did on paper. So practice, get it right. It's either right or it's -2, right? It's really, even though I'm going to have you explain, it's a conceptual question, so you have to explain. Your explanation's basically going to be, I used the right-hand rule, right? Okay. Some students just write RHR, and that's an explanation. But the problem is I can't get partial credit if it's wrong, right? So a little bit higher stakes there. AC RLC series circuit, we did that today. And the transformer, they're more than meets the eye, right? Those are calculation questions. If we had to sort of like, I don't know, rank these or talk about the ones that are like hardest. Well, what's low-hanging fruit? What's like easy, can get the calculation done right away and move on? Magnetic field, current carrying wire, but that could have a right-hand rule in it if there's more than one wire. Faraday's law could be a fairly quick. You do have to kind of figure out like how the flux mathematically is changing. Is it field? Is it area? Is it angle? Something, right? Okay. But then it's just a calculation, right? Get her done. Transformers, step up, step down. Is that a quick or a long, arduous? Pretty quick, right? Just a couple of equations, right? Get it done. AC circuit, AC RLC circuit. Were the AC circuits hard? No. Not compared to other things we've done, right? It's always hard to get your calculator to give you the right answer, right? But like setting up the problem, being able to show me that you know how to calculate impedance and you know like where to put the numbers, right? Even if you make a calculator mistake, I've got your back there, right? Okay, so that one could take a little bit of time just because lots of numbers to put in calculator, but actually mental effort is not that high. I notice that you're not saying things like Lenz's law or force on a moving charge conceptual, right? Okay, so generally, right, transformer, series circuit, Faraday's law, calculation, maybe even circular motion of charged particle, these tend to be the plug and chug sort of, if you've got the equation and you know how to use it, you can get it done, right? So what does that suggest for an approach to this test? What should you do first? Do those. Get them out of the way. Get them done, right? That's points on the board. And then when you need more time on increasing, decreasing, in or out, right, left, right? You can have that time to sink in there, right? So be, and every person's different. Maybe you've got Lenz's law down. It's not hard for you. Great. Get it done, right? Move on to something else. So do that analysis as you start putting together your cheat sheet. Think about the relative difficulty of these problems. Think about the kind of possibilities and anything I could ask you. Get the things down on your cheat sheet that you think you might need to reference. Hopefully you can just look at the problem and do it, and you don't need the cheat sheet, right? I always just needed the cheat sheet to make sure I was getting the formula correct, right? So that's my advice as you go into the weekend and start getting ready for this. Questions, comments, or concerns? All right, get out of here so my 2A students can come in and stress out. Have a great weekend if I don't see you in Grasp.